All right, welcome everybody. My name is Andrea Decker and I have the pleasure of representing the Fleet Science Center for another Sky Tonight talk in the virtual world. Woohoo! Still living in the virtual world. Who would have thought? Close to a year later. So we still can't take the show to the beautiful Heikhoff Dome Theater in the building that you see behind me, that beautiful building over there, because pandemic. But technology still lets us be online, and that's what we're going to do. We'll still keep on bringing you science and astronomy and all the fun things to engage with while we are at home. So for everybody who hasn't been here before, welcome. For everybody who has been with us before, welcome back. Good to see you all. Sky Tonight is a monthly program, happens on the first Wednesday of each month. Normally this side. In our dome, so you can really feel the sky above you. But of course, after this presentation, you can go outside on the street or in the backyard, and you still have the whole sky above you. We just can't fly you from planet to planet like we normally would when we are in the dome. And what else do I need to say? Oh yes, so this is Zoom webinar, not a regular Zoom. So if you would like to interact with me or Lisa, you will have to do that via the Q&A function. It's a little speech bubble icon. You can leave us your questions there at any time. You don't have to wait until we get to the Q&A part. So whenever it pops something into your mind, write it down so you don't forget. The way that it works, Lisa will talk to us a little bit about the news in space science. And we're going to go through the sky tonight. So she's going to show us what we will see when we go out and look at the night sky after this presentation. And then she's going to focus on the supermassive black holes, which is the topic for tonight's Sky Tonight. We will try to take some questions in between those three sections, but we won't be able to get to all of them. So that's why just write them in there and we'll get to them in the Q&A section for sure. And during the Q&A section, I will be pulling up a survey, a little poll. And so if you could take a second to fill that out, that would be great. We always love to hear from our audience, what they think about the event, where they come from, who you are. We always just love to learn more about the people who engage with us. And I think that covers it all. We are recording this tonight, and it will be available on the Fleet Science Center YouTube channel at some point, but it won't be tomorrow. So you'll probably have to wait about a week or two before we make this recording available on our YouTube channel. Lisa, did I forget anything?
I think that covered pretty much everything.
Okay, perfect. The only thing I haven't done is yet to introduce the wonderful Dr. Lisa Will, who is the Fleet Science Center's resident astronomer and also professor of physics at the San Diego City College. So Lisa, why don't you take it away?
Awesome. Thank you so much, Andrea, for that lovely introduction. And thank you so much for all that the Fleet Science Center is doing to keep us all scientifically engaged during the pandemic, even from afar. So as Andrea said, the way we format this show is every month we start off with a little bit of what's in the news. And so I wanted to mention a couple of bits of good news in astronomy. Two current solar system NASA missions have had their missions extended. And so the image on the left is from the NASA InSight mission. It is not a rover, it's actually a lander. And the name InSight implies that it's actually trying to study the interior of Mars. It has had its mission extended until 2022. And it's going to focus more on identifying Mars quakes. It actually has a seismometer on it, and it's identified some. It actually has identified some Mars quakes, and so it's going to be studying the Mars quakes a little bit more. This one is also, some of you may remember, there is a mission that's supposed to do a heat transfer experiment by digging with a mole deeper under the surface, and they've had difficulty with it because what they've discovered is that the soil in this area doesn't have enough friction for it to actually bore into the ground. And so that's going to be a lower priority, trying to get that part of the mission up and running while they focus on some other things. And then the image on the right is from NASA's Juno mission, with that image being taken by JunoCam, with that cameras by Malin Space Science Systems here in San Diego County. And this spacecraft mission has had its mission extended through 2025 or its end of life, whatever comes first. I will say, though, that most of the time, these missions end because we turn them off. It actually is because their funding ends usually before the spacecraft ends, and so this will likely continue all the way through 2025 as it continues to study Jupiter's atmosphere, its gravitational field, and it will include some more targeted observations of the moons, which is not actually what this mission had originally been planned for. So, because it's being extended, they can actually change some of their priorities a bit. So, that's some good news to start off our year with. This was an image that was released recently that I had to share because it's beautiful. This is a famous spiral galaxy, the Whirlpool Galaxy, otherwise known as Messier 51, up in the constellation Canis Venatici. It is located about 31 million light years away. Now, remember, a light year is the distance that light travels in a year. So as we look at this, if it's 30 million light years away, we're seeing it as it was 30 million years ago. But you might notice that this image has a little bit of a different texture to it than you're used to seeing. That's because the Hubble Space Telescope image has the magnetic field of the galaxy superimposed on it. These are magnetic field streamlines detected by NASA's SOFIA aircraft. That's actually an airplane that has an infrared telescope in it. And so when the airplane reaches a certain height, they actually open up the top of the fuselage and aim this telescope out of it. And it's showing how the magnetic field lines actually, you might notice that they get a little bit twisted more around the red glowing things, which are star forming regions. And so it looks like this intense star formation activity might be affecting the shape of the magnetic field in those regions. So I just had to show that to you simply because it looks different, right? It looks interesting, but that interesting different aspect of it is telling us something about the magnetic field of that galaxy. And then there was another recent announcement of this solar system that has 6 planets. I mean, actually, it's there's a lot of stuff going on here. So it's a sextuple star system. So there's actually 6 stars in this system. And over on the left, you will notice that there is a 2 binary star systems that are also orbiting each other. And then over on the right, there is a binary star system that is actually orbiting with the other 2. And so the 2 closer binaries orbit each other every 4 years. And then the larger one orbit is an orbit of about every 2,000 years. These orbits are not quite to scale. But I had to show you this because um, this is the first 6-star system ever found where all of the stars participate in eclipses. We actually can tell that they're all there doing this sort of eclipsing cycle. So it's located around 1900 light years away in the constellation Aerodynas. And I just had to show this one to you because look, it's a system of 6 stars. We get so used to the idea of a star system being maybe like our own solar system with a star and its surrounding planets and asteroids and comets. And then you may have heard that lots of stars actually are in binary systems with 2 stars orbiting each other. And then here's 3 binary star systems that all orbit each other. And so space gets really complicated. That's part of what makes it so fun. And so this is just some of the recent astronomy news from the last month. So now we can start taking a tour of the nighttime sky. And I have this set for what the night sky would look like tonight at the end of the show, basically at 8 o'clock tonight from here in San Diego. Although I don't know about you, but it's looking pretty cloudy out there where I am. So it's good for us to be able to look at the stars here tonight on our screens. To give you a sense of orientation, north is to the very top of the screen and south is at the bottom. East is to your left and west is to your right. And so the center of the screen is basically if you were to go outside and look straight up above you at around 8 o'clock tonight. So I do like to always remind you when we talk of, we always start off with a discussion of the constellations that are above us tonight. And the constellations look like this, right? These are the myths above us in the sky. And so we will mention several of these myths above us tonight. And uh, over a period of thousands of years, these myths have been developed and placed onto the sky as a way for us to sort of get a sense of where we're looking at. It's February, so the constellations above us tonight, we refer to them as winter constellations because they're easiest to see in the winter. And so these constellation myths also enabled people who were telling stories of the sky to have an idea of time of year, to know where they are in the sky. Also allows you to get a feel for time of night, if you're watching the sky carefully. But when you and I go outside tonight, we don't see these images of these creatures up on the sky. We mostly connect the dots. And so when I show you the constellations in here when we take our tour, we do it the way the human brain actually does it, which is connecting the dots on the sky, because the human brain likes to look at things and make patterns. And so we will discuss some of these patterns up here above us in the sky tonight. So here are the stick figures. Some of these stick figures have had more cultural importance over the years than others. And so we'll start off by talking about those. But before that, I'm going to put this green line up here. There's this line going across the sky. And if you look carefully, you'll notice that there are months of the year next to that green line, and that February is below the western horizon. And so you might be wondering, why is February below the western horizon if it's February right now? Well, that's because this is the ecliptic. It's the apparent path of the sun on the sky. And by 8 o'clock tonight, the sun will have already set, because what we are seeing labeled here is the location of the sun on any given day of the year. Now, we know that the sun is the center of our solar system and that we're actually moving around it. So, as we orbit the sun once a year, we see the sun go through a complete circle around our celestial sphere from our point of view in that year. And the constellations along that path have gained cultural importance because they are the constellations that the sun moves through. Also, where the moon moves through. You don't see the moon here because it's not going to be rising till about midnight tonight. And also, the planets move through this. And in fact, there is one planet that is visible to the naked eye when you go outside tonight and take a look up in the sky, up in the constellation Aries, and that's Mars. So before we start going through the stories of these constellations, let's take a look at Mars briefly. And I do want to show you this beautiful image of Mojave crater on Mars. This was put up on Twitter by Sean Duran from using HiRISE data. What's HiRISE? HiRISE is a camera on NASA's Mars Reconnaissance Orbiter spacecraft, which has been taking amazing images of Mars for years. And you have enough data from it that you can actually kind of, instead of looking at it straight down, you can get a sense of altitude here. And so Sean Duran does amazing images from this data. And so this really makes it, I mean, if I had told you this was out, oh, here in the Imperial Valley somewhere, or, you would have been like, oh, that looks familiar, right? Out in Anza Borrego, but this is actually Mars. And one of the reasons why Mars is of such interest to astronomers and to NASA is because it is so Earth-like. When you take a look at this, you feel a bit at home. Of all of the planets in the solar system, it is the one most similar to Earth, which is why we visited there so frequently. And our next visit actually happens this month. And so the Mars Perseverance rover will be landing on March 18th if all goes well. So, similar to Mars Curiosity, it is going to experience 7 minutes of terror as it goes through its landing cycle, where a parachute will be deployed, and then they're going to use a sky crane again to actually set the rover down. Um, Mars is actually really hard to land on because it doesn't have much of an atmosphere. It has an atmosphere, okay, but it doesn't have much of one. So, with the smaller rovers like Spirit and Opportunity, a parachute was enough. But for Curiosity, Curiosity is a science lab the size of an SUV. Think of it that way. And so this is also another large rover. It needs a little bit of extra help. The parachute isn't enough to slow it down because when it enters the atmosphere, it's going to be going at about 12,000 miles per hour. So it's going fast and it has to slow down to try to make a gentle landing. The moral of the story here is landing on Mars is hard. And I remember how terrified all of us were watching when Mars Curiosity landed, hoping that it went okay. On the 18th, when this occurs, Mars is going to be about 11 light minutes away, if I recall correctly. Yes. And what does that mean? That means that it takes 11 minutes for us here on Earth to receive a signal from Mars. So we're not going to know till 11 minutes later if this thing worked. And so in March, I will keep you updated on how this went. This is kind of an interesting mission. It has a sort of a proof of concept object on it. It has a little Mars copter to see if they can actually design a helicopter that can, and it would be for a small, so think of it more like a drone that can operate in the very thin atmosphere of Mars. So hopefully we will have good news for you next month. Keep your ears open for news about the Mars Perseverance lander. And Mars is up in the constellation Aries tonight, which is one of the signs of the zodiac. You have probably heard of the constellation Aries. And in fact, the ecliptic actually passes through the signs of the zodiac. That's why the signs of the zodiac became important, because they're the constellations that the sun moves through. So let's start our tour of the nighttime sky by going through the signs of the zodiac from west to east, starting with Pisces. Pisces is known as the two fishes. The V that it makes is usually depicted as a cord or water emanating from the mouths of each of the fish. This is associated with a myth from ancient Greece, where Aphrodite and her son Eros, they were either shapeshifted into the forms of two fish to escape, or two fish rescued them at some point. But this is part of an Aphrodite myth. That's where the two fish are from up on the sky. The next sign of the zodiac over to the east is Aries. Aries is known as the Ram, and it's not a very bright overall constellation. The brightest star in Aries is named Hamal, and it's located about 65 light years from our solar system. So if you go outside tonight and you see a Hamal in Aries up in the sky, you're seeing it not as it is, but rather as it was about 65 years ago. And although when I look at this, when you see it connecting the dots, I don't see a ram, but it has been known as a ram since Babylonian times. So the myth of this being a ram has been around for a long time. Before that, sometimes it was referred to as a farmhand. But different cultures assign different stories to these parts of the sky, and so these stars in Aries, for the myths from the Marshall Islands, for example, represent a porpoise. Now let's move on to the next sign of the zodiac over to the east. Unlike Pisces and Aries, which are a little faint, Taurus, the bull, has a lot of very bright stuff going on in it. So it's actually one of the easier signs of the zodiac to pick out on the sky. The red star next to the T in Taurus is Aldebaran. It's an example of something called a red giant. So it's a star that has um, that's evolving. It has expended the nuclear fuel in its core, and it's starting to burn through some hydrogen and helium in its outer layers, and its outer layers have expanded and cooled. And so red because it's gotten cooler, and a giant because it's gotten bigger. And it is also about 65 light years from our solar system. There is, and it is, there is a V that makes the face of the bull, which is kind of hidden by the T in the word Taurus here. And that is a group of stars known as the Hyades, which is the closest what we call open cluster to our solar system. It is a young cluster of stars located about 150 light years away. And then there is above the U in the word Taurus, the second U, I guess I should say, in the word Taurus there, you might notice a little tight bunch of dots right above them, and that is the Pleiades, which is another open cluster. It's a famous open cluster named after the seven sisters from Greek mythology. And it looks like a tiny little dipper up in the sky, but it's not the little dipper, which is far to the north from here. And it has a couple of hundred stars in it, but to the naked eye, you can only see about 7. And in fact, usually it's easier to see about 6. Being able to see the 7th with the naked eye has often been considered an eye test. But if you have a pair of binoculars, I love going out and looking at the Pleiades. It looks like diamonds spilt on black velvet, a very pretty young group of stars up in our nighttime sky. The next sign of the zodiac over to the east is Gemini, named after the twins Castor and Pollux. And so the two bright stars that you see there that look like twins up in the nighttime sky, those are Castor and Pollux. Those are famous twins from Roman mythology. But in fact, this part of the sky, once again, these stars have been known as twins, predating Greek and Roman mythology. In fact, this part of the sky was referred to as the Great Twins by Babylonian astronomers. Now, what I like about these is because they actually really do, to me, look like twins up in the sky. They look like identical stars, but they have nothing to do with each other. They aren't gravitationally close to each other. This is not a binary star system. In fact, Castor is about twice as far away from our solar system as Pollux is. And I use that as an example of how you don't have good depth perception on the sky because not all stars put out the same amount of energy. Not all stars put out the same amount of light. So you can't actually judge how close or how far a star is from us by looking at the light up on the sky. In fact, many of the closest stars to our solar system are so small and so cool in temperature relatively that we don't see them with the naked eye. And I've always found that fascinating that out of about the closest couple dozen stars to our solar system, we can only really see a handful easily with the naked eye. And so that's Gemini up in the nighttime sky. Next sign of the zodiac over to the east is the constellation Cancer. Let me go back real quick. Okay, I want you to notice how to the left of Gemini, see how faint that is? And we're putting a constellation there. So you might be saying, why those stars? Why did you pick them? Because the sun travels through them, right? And so once again, it's the fact that the ecliptic goes through this part of the sky that makes this part of the sky important. So Cancer is really hard for us to find up in the nighttime sky from a metropolitan area like San Diego. So my suggestion for you to tonight would be look to the east of Gemini to try to find it. Now Cancer is the crab, and it is part of the Hercules or Heracles myth, depending on if you're talking about the Roman or Greek version. This is a crab that bit Hercules as he was trying to slay the Hydra. He got upset at it, so he killed the crab. But Hera, who was not a fan of Hercules, said, well, you know what? You didn't like that crab, so I'm going to put that crab up in the sky so you can see your enemy amongst the stars forever. And sometimes when I read through these constellation myths, there's a lot of revenge myths up here on the sky. It's really kind of funny to me, but that's why That's where Counts of the Crab comes from. It comes from the Hercules myth. And then the last sign of the zodiac I want to point out to you tonight, rising over in the east, is Leo, the lion. The brightest star in Leo is at the base of that little backwards question mark that marks the front of the lion. And so Leo is a fairly bright constellation that you can pick out in the sky, even from a large metropolitan area. So, yeah, so if you want to go look for the constellation Cancer, look in between Gemini and Leo. That's probably the easiest way for you to do that tonight. The brightest star in Leo, Regulus, at the base of that backwards question mark, is about 77 light years from our solar system. And when we go back through our history, Leo is one of the earliest constellations that we see recorded. We have it going back almost 6,000 years at this point. It's dated back to about 4,000 BCE. And it is very frequently by different cultures referred to as a lion, which is one of those things that I find really interesting. The sort of uh, when people connected the dots, they connected the dots in the same shape and told the same story about it. So, those are the signs of the zodiac that are visible tonight at about 8 o'clock tonight, marking the path of the sun across the sky. Now let's pick out a few more constellations to talk about. We have Cetus, which is either depicted as a whale or a sea monster. Another one that's taking up a large part of the sky without a whole lot of bright stars. The most interesting star in Cetus is the star Mira, which is one of the earliest recorded variable stars. A variable star is a star that varies in its brightness, and Mira is one of the ones that does so with a regular periodicity. And so it was noted for that. Taking up a large part of the southern sky is Aerodynas, which is name comes from an ancient Greek name for the Po River. It is the sixth largest of the 88 constellations that are in use by modern astronomers. And its brightest star, Achernar, is its name comes from a word that means the river's end. So it has one of the more, in my opinion, one of the more poetical names for a star up on the sky. And it's about 140 light years or so from our solar system. Probably the most notable and easy to find famous constellation up in the sky tonight is Orion, the Hunter. Its blue star in its bottom right foot is Rigel, located about 700 or so light years from our solar system. And the bright red star up in Orion's left shoulder is Betelgeuse, a red supergiant located about 500, between 4 and 500 light years from our solar system. That's the one that we were all excited about last year, hoping it was going to blow up as a supernova, and it didn't, but there's still time. It is in its red supergiant phase of its life, which means that it's close to the end of its life. And it's expanded in size so much that if you were to put Betelgeuse in our solar system where our sun is, Mercury, Venus, Earth, Mars, and the asteroid belt would all be inside of it. Its outer layers reach almost out to the orbit of Jupiter. So it's absolutely huge. And like I said, it is when I get asked, can you point to a star in the sky and say that one's most likely to go supernova next? It's always Betelgeuse that we pointed to. And last year it decreased in brightness greatly, and it's gotten brighter, almost back up to its normal brightness again, but which is kind of disappointing. I'm personally hoping it'll blow up because it would be so bright we would be able to see it even during the day. It'll blow up in something we call a supernova, which I'll mention again later. And then the three bright stars of Orion's belt, they look like triplets up in the sky, but it's once again a case where you don't have good depth perception because the middle star of the belt is about twice as far away as the other two are. And so that's Orion the hunter up there on the sky tonight with his trusty hunting dogs, the smaller dog, Canis Minor, with its bright star Procyon, and the bigger dog, Canis Major, with its brightest star, Sirius. Now, Sirius is often referred to as the dog star, and it is the brightest star visible in the nighttime sky from the Earth. And it's bright for two reasons. One, it's actually relatively close to us. It's not the closest star to our solar system, but it's only about 9 light years away, making it one of the brighter stars in our solar system. Excuse me, one of the brighter stars close to our solar system. And then not only is it a relatively close star, but it's a hotter star and slightly larger star than our own sun. So it's putting out more energy than our sun does. And so its name comes from a word that means glowing or scorcher, sort of a testimonial to the fact that it's been known to be the brightest star in our evening sky for a long time, for a long time. And Canis Major and Canis Minor are supposed to be helping Orion hunt Taurus the bull. But there is a bunny rabbit up on the sky, Lipus, and this rabbit does not appear obviously in any of the Greek myths, although this is a constellation that dates back to the second century when these constellations, a lot of these constellations had been originally cataloged. So in my head, I always think that those dogs are actually going after the rabbit where, and leaving kind of Orion on his own to go after the bull, because that's just the kind of things that dogs do. But if any of you ever can find out definitively what rabbit this is supposed to be, you let me know. You let me know. One of the constellations up there in the nighttime sky that you might not have heard of is Monoceros. It's a unicorn, Monoceros, one horn. And this is not what we would call an ancient constellation. To astronomers, this would be a modern constellation, which means it dates back to the 17th century because, modern is a relative term in astronomy. It's not easy to see in the naked eye. It dates back to a catalog that was put together purposely to connect the dots between some of the fainter stars in the sky, because it was known that when the Greek astronomer Ptolemy put together a catalog of 48 constellations, and many of them we still use today, he focused on the brightest stars. But constellations have not been traditionally used just to tell stories or to tell time. For astronomers, they're also used to tell location. And so, as we wanted to catalog more observations and be able to communicate them to each other more precisely, we needed to designate some of the fainter regions of the sky to constellations as well, so we could use them as locations. And so, although Monoceros itself is not easy for us to see up there in the sky with the naked eye, it is home to some very lovely deep sky objects that are only visible with telescopes. But if you've ever heard of the Rosette Nebula, one that's named because it looks like a rose, that's up in Monoceros. So far, these constellations have all been south of the ecliptic. Let's go north of the ecliptic. Here's Perseus, another hero from Greek mythology. And one of the more interesting stars in Perseus is the star Algol, which is yet another one of those variable stars. It was once again one of the first variable stars to be discovered. The name Algol is shortened from Raj Algol, which is a demon. And so it was known as the demon star, and it is an eclipsing binary, which means it changes in brightness because the stars take turns going in front of each other from our point of view, located about 90 light years from our solar system. There's also the constellation Auriga up north of Orion in the sky. So if you take a look north of Orion, you'll see a bright star, and that's Capella, the brightest star in Auriga, located about 40 light years or so from our solar system. And what I find interesting to think about as I look at Auriga is that it is the home, if we wanted to say it fancy, the home of the galactic anti-center. All right. So the center of the galaxy, well, that would be the galactic center. The galactic anti-center means we're looking directly opposite the center of the galaxy. We live in the Milky Way Galaxy, which is a spiral galaxy, which is flattened like a pancake, kind of looking like that pretty picture with the magnetic fields from earlier, if we could see it in this direction. But if we see it edge on, You can imagine it being flat like a pancake, and all the stars are like chocolate chips in the pancake. In the summer, we are just one of the chocolate chips, correct? Here in our solar system. Um, our solar system is not in the center of our galaxy. It's not on the very edge either. We're about halfway out. In the summertime, when we're looking up at the constellation Sagittarius, we're looking directly towards the center of our galaxy. What's opposite Sagittarius in the sky? It's this part of the sky up in Auriga. So instead of looking towards the center of our galaxy, we're looking out from the center of our galaxy when we look up at that part of the sky. So it can always be difficult to get a good spatial orientation of where we are in the universe. So that's another way to think of it. We're looking opposite the center of the galaxy when we look out at the sky tonight. Camelopardalis, there's a giraffe up there on the sky. Camels have long necks, leopards have spots, and so a giraffe has a long neck and spots. And so this is sort of made up of the Greek words for camel and leopard and shoved together to make the word Camelopardalis. And this is one of those constellations that was developed in the 17th century to take up some of the faint parts of the sky, as was the constellation Lynx. Not necessarily associated with any myths, but it's comprised of such faint stars. The idea is you would need the eyes of a lynx to see it. And so that's where the name of that comes from. And so that these are some of the stars and constellations that are above us in the nighttime sky. I haven't looked at any of the questions. Should I answer any of the questions now or should I keep going?
I think one question that we should take now
Mhm.
is why doesn't convection mix the fuel in stars' core and upper layers?
All right, so that is an interesting question. So there are three ways by which energy is transported. We have conduction, which is like if you set your hand down on like the top of your desk and it feels cold to you, that's because your hand is hotter than the desk. You're feeling that temperature difference, but you know if you leave your hand there long enough, no longer feels cold, and that's because heat has flowed till the temperatures became the same. All right, to bring them to the same temperature. That's conduction. Convection is what goes on when you boil water. Those bubbles form at the bottom of the kettle and they rise up to the top, and so you're getting the mixing of materials. And then radiation is energy transport by light. It does not need a medium. It does not need materials to be in contact. And so the question was, why doesn't convection um, mix the
The
fuels
fuel in the star's core and upper layers.
all right, so convection actually does play a role in the star's upper layers. We can actually see convective cells in the sun's surface, and so the way our sun is structured, if we could cut open the sun and look at it like it was an onion, the core would be where energy is being created. I shouldn't say created. Nuclear fusion is producing energy in the sun's core. Um, and then that energy starts radiating outward in the form of high energy light. And then it heats up the gas surrounding it that is not doing nuclear fusion. But as it heats up the gas around it, it does start making these convective cells that rise and fall. And we can actually see that in our sun. So convection does play a role in our sun and in other stars, as well.
Great,
So,
thank you.
so hopefully that helps with that a bit.
Okay, then let's go on and we'll take all the questions then after the black holes because there's some questions about black holes and one that we can also answer later. So
All
let's do
right.
that.
Awesome. All right. So, what we've done so far is we've taken a tour of the sky by looking at the bright stars. But you may have heard of black holes, which are not bright at all. And so, what are they? And you may have even heard that there's a supermassive black hole at the center of our Milky Way galaxy. And so, tonight we wanted to talk about supermassive black holes in particular, what they are they dangerous, and do all galaxies have supermassive black holes in their centers, or is it just the Milky Way? So, how do black holes form? Well, we already mentioned that stars are doing are producing or basically producing energy by doing nuclear fusion in their cores. And then once they run out of hydrogen in their core, they can start fusing helium and some other materials in their outer layers until they get to a point where they can't do fusion anymore. And so for stars like our sun, which are low mass stars, they will fuse hydrogen into helium, then helium into carbon, and then stop because they are not hot enough and dense enough in their centers to do fusion past that. High mass stars like Betelgeuse, they can actually continue fusing all the way up to iron. But once iron builds up in their core, nuclear fusion no longer naturally occurs. And at that point, a bunch of processes happen really quickly, and the star makes a supernova. It explodes. And so here are a couple of images of supernova 1987A, named because it was a supernova that we observed in 1987. Astronomers were pretty obvious in our naming, okay? And so what we have is two images of the same part of the sky. The one on the left is the during the supernova, and then the one on the right is what it looked like without the supernova going off. And so in February 1987, a supernova exploded from our perspective. And it happened relatively close by, about 150,000 light years away in a neighboring galaxy of our own Milky Way called the Large Magellanic Cloud. And it was bright enough that you could see it with the naked eye for over a year. And it is the closest supernova that has happened in centuries, like literally centuries. Um, Supernovae don't happen all that often. And so I did want to show to you though that supernovae are bright enough that we can observe them even in other galaxies. And so this is an example, an artist representation of what supernova look like going off in other galaxies. Supernovas are bright enough that they can temporarily outshine the entire galaxy that they are in. So we can see them at large distances. And that's great because supernovae are rare enough that in this current epoch of the universe, the rough rule of thumb I remember is that they only happen about once per century per galaxy. So why do I mention supernovae here? Well, the largest of the stars that make supernovae, they leave behind black holes. What happens to their leftover dense cores, where all of the nuclear fusion had been, or where the nuclear fusion had been occurring. So what are black holes anyway? Well, let's take a little moment to talk about relativity. In the early 1900s, in 1905, Albert Einstein came up or published the special theory of relativity. The important thing about black holes to remember from special relativity is that Einstein argued that nothing could go faster than the speed of light, that the speed of light was a cosmic speed limit. And then in 1915, he published his work on general relativity. And General relativity said everything, including light, was affected by gravity. So that, when you throw a baseball up, it falls back down. But if you point a laser pointer up, it doesn't. Well, it actually does. It's just the Earth's gravity is pretty tiny. So we don't see it fall right back down. But gravity can cause light to bend by warping the space around it. So if you were to ask that particle of light, that photon, if it made a turn, it would say no. It would say I was following a straight line. It's just the path itself it was following curved. Now, I always like to remind my students that we take it for granted that we look back at Einstein and we think, oh, he was smart, and people kind of revere him in a strange sort of way. But they people thought that he didn't know what he was talking about, basically. So what we're seeing here is an artist representation of a test of general relativity that happened in 2018 during a total solar eclipse. You could predict that during a total solar eclipse, there should be a star behind the sun. So that's what's labeled as actual position of the star. But if general relativity was correct, the light should bend around it, just like if you were arcing a baseball for someone to catch. And so if that light actually bent around the sun during that total solar eclipse, we'd still be able to see that star. And we did, because it would look like it was at that apparent position in that straight line from the Earth. And by that time in the early 1900s, we already were able to catalog stars by their spectra. So it wasn't just like, hey, there's just some random star in that location that fooled us, right? And so general relativity, the fact that gravity could bend light, actually then predicted the existence of black holes, because black holes are objects whose gravity is so great that not even light can escape. Another way of thinking about it is that if you could stand on a black hole, you can't. But if you could stand on a black hole and you pointed your laser pointer up, the dot would fall on the ground by your feet because the light would come straight back down. That's one way kind of thinking about it. So, do we know of any black holes? This is an interesting star system here. Just this past year, this is actually a story from 2020. This black hole was announced, its discovery was announced, and it's just about 1,000 light years from our solar system. In fact, this was the closest black hole known to our solar system at this point. And it was one of the very first, what we're going to call stellar black holes. And I'll mean that, I'll explain what I mean for that in a few minutes. That was found by watching a couple of stars orbiting around it. So you might notice you see two stars here that look like they're orbiting something, but you don't see anything there. That tends to be the primary way by which we found black holes so far, because you can't see them because they're not emitting any light. So you look to see how they affect their environment. So this is an object, a black hole that's located in the constellation Telescopium, which is visible from the southern hemisphere, located about 1,000 light years away. Now, I call these stellar mass black holes because we just said black holes can be made in supernovae from the deaths of high mass stars. And so they're usually about anywhere between the black hole left behind is usually anywhere from about 10 to 25 or so times the mass of our sun. So we have those. But then the next type of black hole that tends to be common are these supermassive black holes. And by supermassive, we mean like huge, like about 1 million times or more the mass of our own sun. I actually think the lower end they're about 100,000 times the mass of our sun. So we go from like a couple dozen times the mass of our sun to 1 million times the mass of our sun. So how do we look for those typically? Well, this is a depiction of the event horizon and the accretion disk around a black hole. The event horizon is the distance from the singularity, the collapsed object, the black hole itself, from where not even light can escape. So what you're looking at in this depiction, that black hole in the center is not the black hole, but it's the region around that dense compact mass where not even light can escape. But stuff could still be orbiting it. Like if our sun were to turn into a black hole, it won't. Of the same mass, it can't. But if there was suddenly now a one solar mass black hole in the center of our solar system, the Earth would continue orbiting it just the way it is now. It's just that in about 8 minutes after we replaced it, it would get cold because there'd be no more light coming to us. Okay. So black holes can have stuff orbiting them. And that tends to be how astronomers look for the presence of black holes. So, um, how does this help us? How does the fact that material can orbit a black hole help us locate them? Well, for one thing, if there is this accretion disk of material that can that is orbiting around a black hole, that material falling into the black hole, creating a magnetic field that can direct jets of material. We can observe this region around it because we can observe the jets of material coming out of this accretion disk, and we can often observe flares or something like that in the accretion disk itself. So we should be able to see something that looks like this. And so the question is, have we? And the answer is yes. This is Messier 87, a very large galaxy in the constellation Virgo. And we see jets of material coming out of its core. That jet that you're seeing coming out of that bright core, it's about 4,000 light years long, moving at relatively relativistic speeds. And the black hole in the center is absolutely huge. And we'll actually talk more about that one later again. So we think this is a jet coming out of the region around the supermassive black hole at the center of this particular galaxy. How do we get the masses of these supermassive black holes? So this is, I know you're just looking at it like, why are you showing me this sort of rainbow squiggle? So as this accretion disk is orbiting the black hole, it's going around. So I can take a look at it being red shifted or blue shifted in terms of its Doppler shift. The part that's spinning towards us, we would see its light get blue shifted. The part that's spinning away would be red shifted. And then the green line there is showing sort of the neutral. It's the part that's not moving towards us or away from us at this point. So the Doppler shift allows us to figure out how fast something is moving. It's the same physics that actually gives you speeding tickets, believe it or not. It's just using different wavelengths of light. So how far to the blue or how far to the red the light is shifted gives us an idea of how fast this object is spinning. How fast it's spinning tells us what the gravitational pull is on it that's making it move. And if I know the gravitational pull, I can determine the mass making that gravitational pull. So we get the masses of supermassive black holes by looking at how fast the material is spinning in the accretion disk around them. And so what we have been able to discover is that black holes at the centers of galaxies tend to scale up with galaxy size. Kind of makes sense. The larger the galaxy, the larger the supermassive black hole at the center of it. And so, what you're seeing here is not very exciting images, but those are Hubble Space Telescope images trying to look deep down into the cores of these galaxies. And so, you're seeing to scale, the smaller galaxy has a estimated 3 million solar mass black hole at the center, and the larger galaxy up at the top has a 2 billion solar mass black hole at the center of its galaxy. This is another one of the interesting news stories from last year about black holes. What you're seeing here is two supermassive black holes locked in a dance. There is one black hole, the one that's kind of sitting still, showing the event horizon. That's about 18 billion times the mass of our sun. And then the smaller one sort of dancing around, well, that's only about 150 million times the mass of our sun. And where it's crossing through, they're orbiting each other, but the heavier one appears fixed. And when it crosses through the accretion disk, it's causing flares that were detected by NASA's Spitzer Space Telescope. And so this is an interesting artist representation of what we think is going on in the center of that galaxy where a merger must have occurred. And then in the center of our own galaxy, this is data put together by the UCLA's Galactic Center Group. And so what you're seeing here, all those colorful blobs that are moving around, those are stars near the center of our galaxy. And you're seeing their orbits. And so let's see, is this going to play again? It's playing again. So I want you to notice how fast they're kind of looping around. And then the timestamp, the year is up at the top right. And so you'll notice that we're seeing these stars at the center of our galaxy, so about 26,000 light years away from us, orbiting the center of our galaxy over a period of a few years. Now, I want you to remember it takes Saturn 30 years to orbit our sun once. And so for these stars to be orbiting the center of our galaxy that quickly, that means they have a large gravitational pull tugging on them. So you see that white star shape? And you'll notice that that's just a marker. There's no star there. What we can do is we can estimate that's the center of our galaxy. What is the mass it must have for all those stars to orbit it that quickly? And when you do that, you get an estimated mass of 4 million times the mass of our sun, or 4 million solar masses. And that is the estimated mass of the supermassive black hole at the center of our galaxy. And this work is considered to be so important that, in particular, Andrea Yes from UCLA's Galactic Center Group was given the Nobel Prize in Physics this past year, along with Reinhard Genzel, for the discovery and understanding of the supermassive black hole at the center of our galaxy. And I do have to make the comment now that when Professor Yes or Professor Gez got this Nobel Prize, that means we got 4 women with Nobel Prizes in physics now, a whopping 4 women. Anyway, I'll continue. So those are some indirect ways in which we have seen black holes at the centers of galaxies. But you might remember from 2019, there was a very interesting result from the Event Horizon Telescope, which is a collaboration of telescopes all over the world to give us an image of a black hole. Now, this particular black hole is at the center of M87. Remember that one with the jets coming out of it? That galaxy is a huge galaxy. And because it's a huge galaxy, it has a huge black hole at the center with estimated mass of over 6 billion times the mass of our sun. And so, even though this galaxy is 55 million light years away in the constellation Virgo, it's actually easier for us to try to image this black hole than the one at the center of our own galaxy for a couple different reasons. But so, what was observed at this time was the way the light would be bent around the black hole. And so what you're seeing here is a simulation of what the black hole should look like with the light bent around it. And then this is the image. And so this image that the Event Horizon Telescope got was basically you can see it matched the simulations quite nicely. And so this is very consistent for what this black hole should have looked like for us to be able to image it, predicted by general relativity. So we know that we have these supermassive black holes at the centers of galaxies, but where do they come from? So two competing ideas. One of them is that they're made by black hole mergers early on in the history of the universe. So this is data from the LIGO Gravitational Wave Observatory that has been looking for gravitational waves produced by black hole mergers, and it has found them. So we know black hole mergers do occur. And in fact, we know that as they merge, they make even bigger black holes, including uh, a discovery in 2019 of finally something called an intermediate mass black hole. So that one up there in the blue that's about between 140 and 160 times the mass of the sun, that's bigger than you can make from the death of a single star. So we know it had to be made from mergers. And then we think if you can continue scaling those up, you might be able to make supermassive black holes. The other option for making supermassive black holes is that as a black hole formed at the center of a galaxy, as the galaxy was forming, it just started eating up a lot of the gas and stuff falling into it. And just if you throw something into a black hole, you just get a bigger black hole out of it. All right. So when you take a look at beautiful images like this of galaxies, I want you to think now, we think pretty much every large galaxy has a supermassive black hole in the center of it. And so that's a quick tour of supermassive black holes.
Awesome. Thank you so very much,
You're
Lisa. I
you're
appreciate that.
welcome.
Also, now I have questions about black holes merging and eating everything around them until there's only one big, massive black hole left in the whole universe.
Probably not going to happen because remember, you still have to be close enough to fall in. So,
Yes,
like that supermassive black hole at the center of the galaxy, we're good. We're fine out here.
perfect. Very
Okay.
good.
Okay.
Otherwise, I see a movie coming. All right, so we're going
Yes.
to get started with the Q&A, and I can already tell we're going to be a little bit over time. So,
Sorry.
but if that's okay with the audience, sure is okay with me. And I got to start with something that Karen sent in because how can we not kick off the Q&A with a good old humor? And she said, "What did two black holes say when they collided? Nothing. They just waved." And I thought that is just perfect. Thank you, Karen, for sending
Oh,
that in.
wow. Nice nerd joke, Karen. Nice
Right?
nerd joke.
Love it. So, can we see black holes?
You know, depending on what you mean by see, we could directly detect them with gravitational waves, but they don't themselves emit light. The material around them can emit light, and that we can directly observe as with light.
So, but we won't be able, if we go out tonight, we won't be able to see a black hole in the
Nope.
sky.
Unfortunately.
Well, Andy would like to know, why do black holes have an accretion disk?
That's a great question. And so the there's a couple different ways we can think about it. But when stars form, they after the very first generation of stars, they tended to form with stuff around them. So think of our own solar system, right? We have the sun, but we also have planets and comets and asteroids and moons. And so if our sun were to turn into a black hole, that stuff would still be orbiting it. Um, the stars that tend to make black holes are high mass stars. You might think the bigger the mass, the longer their lifetime because they would have more fuel, but because they're so massive, they tend to run at a higher temperature. So the fusion reactions go quicker. So the higher the mass star, the faster they burn through their fuel. And so many times they're still surrounded by some of the gas and dust that they recently formed out of, because some of these stars have lifetimes only of about 1 million years or so, as opposed to the 4.5 billion year life of our sun. So it is natural for there to be stuff surrounding a star that can form these accretion disks.
Thank you. And then someone would like to know, how far away from Earth is the nearest black hole?
About 1,000 light years away, and that was the discovery. I think it was just last May. Up till before that, it would have been closer to about, or it would have been more like 1,500 light years away. But we think of it as being about 1,000 light years away. Now is the closest one.
Thank you. And then, how fast can a black hole travel?
This is the
Can
sort of
it
thing that can
travel?
give you nightmares if you think about it too much. So black holes, because they do form from supernovae, they were just stars. They can continue on in the orbit that their star had. So they can still move, so they can still travel. In fact, there's some evidence that some supernova explosions can be asymmetric and actually give them a kick, so it could start running away even faster than it had been moving before. So yeah, black holes can move. It's hard to, when we measure speeds, it's always a question of relative to what, because you don't tend to think of our sun as moving because you think of it as standing still and us orbiting it. But our sun is orbiting the center of our galaxy about once every 220 million years. And so everything out there is moving, and the black holes that form will move as well.
Amazing. I had no idea.
Yeah, I know. And
Colleen has a
Andy wouldn't see it coming. So that's the kind of thing that should
exactly.
give you nightmares. That's the sort of thing I like to tell you all before.
Great. Colleen has a great question. Is there anything inside? I mean, they're all great questions, but it's one that I'm interested into. Is there anything inside of a black hole? Because when we look at sci-fi, we say we can use black holes for traveling to distant areas of the universe. So, is there something in there, or can we go in there and time travel? Like, how is that going to work?
So I'm going to say that we can speculate about what the inside of a black hole is like, but we can't really say for sure because to test it, for the most part, we would need to craft an experiment that could give us information. And by definition, a black hole doesn't like to give us a lot of information. So I can't say what's inside the black hole, like everything that falls into it. Although it gets tidally distorted, it gets broken up as it's falling inward. But if I were to add our sun to a black hole, the black hole's mass would have increased by almost exactly the mass of our sun. So everything that falls into it is its mass still has a gravitational effect on the universe. What form or what it's doing once it's in there, it's hard for us to actually craft a scientifically valid hypothesis to test. Is that okay?
Yeah, I think that is okay.
It sounds weird to say, like, I don't, who knows, but it's fun to think about, but it would be hard to be able to say for sure.
Do you think we'll ever find a way to?
I don't know if gravitational waves can give us enough information because the gravitational waves we're detecting actually come from the mergers, not from the individual black holes or neutron stars for that matter themselves. So yeah, right now there's no way for the inside of a black hole to communicate out to us.
Yeah, okay. So when we talk about things falling into the black hole, how close do you have to be before you fall in? Or how close can you be before you fall in?
Um, well, there are going to be There's multiple distances that we can talk about. There's the event horizon where once you've fallen in, you can't communicate back out, right? Because light can't escape. But there's also going to be the point from which you get spaghettified, right? Where the gravitational force actually stretches you out and starts to destroy you. And we have had observations that indicate stars being broken apart falling in. So there's going to be, and that all those distances are going to be dependent on the mass of the black hole as well. So I can't say you can get exactly up to here before falling in. That image of the black hole from the Event Horizon Telescope, that sort of red blobby thing, that was about 2.5 times the size of the event horizon. So, and then the accretion disk would likely be even a little bit further out than that. But those are smaller particles typically than we are to exist out there comfortably. In fact, some material in an accretion disk can be made from the stuff that gets broken up on its way fallen in.
Fascinating.
Yeah, black holes are fun.
Yeah, they really are.
Yeah.
And Eric would like to know, can black holes die?
Yes. There's something called black hole evaporation, which isn't evaporating like, leaving water outside or something like that. But the time scales are so slow that a black hole that would have formed at the beginning of the universe would still be around today. So, a stellar mass black hole, I think the estimate is the number of years would be a one with about 100 zeros after it in terms of years, a very, very, very long time. So yeah, they can die that. So it's a question of a practical or theoretical. Practically, no. Theoretically, at some point, yes, they will.
Interesting. It's good to remind oneself there's the theoretical and the practical oftentimes in science, right?
Yeah, yeah.
Karen is wondering, when two black holes spiral in and merge, at what point are they merged and stop sending out gravitational waves? When the event horizons contact or some other point?
That's a really interesting question. I'm trying to think of the best way to explain that because the waves are actually being produced by their gravitational interaction as they fall in. So when they do merge, the gravitational waves stop being sent out that way. And the gravitational waves are not dependent on the event horizon, so we can detect them. So I think, and I'm not a black hole theorist, but I think it's when they actually physically merge.
All right. Colleen was wondering, does the release of Hawking radiation depend on the size of the black hole?
Okay, so that actually kind of gets us back to the whole idea of the black hole evaporation as well. And as far as I know, the rate is not dependent on the mass of the black hole. I could be wrong, but I don't think it is. I think Hawking radiation has a different dependence.
Got it. And then Peter was wondering, will that sextuple system you showed earlier eventually create three black holes that will orbit each other until they merge to create one massive black hole?
If I recall correctly, the stars in that aren't likely the ones that are going to make black holes. So
So they're not
I don't
hot
think so.
enough.
Yeah.
Okay. And then Susie was wondering, can astronomers, in quotation marks, see black holes in other wavelengths beside the visible spectrum?
Yes, in fact, a lot of the work done by the UCLA Galactic Center Group is actually in radio waves because radio waves travel easier through the gas and dust at the center of our galaxy to communicate back out to us.
Wonderful. And then, is there anything that can't get pulled into a black hole? Is there any matter that's too light or too small?
The only sort of known, there's no matter, there's no material that can't get pulled in. Light can get pulled in. So I'm thinking we're pretty much stuck getting pulled in.
Okay. No matter, there's no escaping a black hole, clearly.
Pretty much.
Yeah. Okay, with that, we're coming to the last question. It's actually a story that Colleen shared with us, and I really appreciated her doing this. So she had the chance to go to Death Valley recently and do some real stargazing, because Death Valley is one of the dark sky sites in the world. So she was incredibly moved by seeing the Milky Way for the first time. I think I can relate to that feeling because last year was the first time I saw the Saturn rings through a
Oh yeah. Yeah.
telescope, and it just, like her, I just teared up. It was really weird.
Yeah.
Started crying about seeing Saturn, but I did. So she was wondering, even in Death Valley, it was pretty difficult to make out Milky Way. So do you have any recommendations for places in California that offer great views of the Milky Way?
So, in terms of Southern California, usually we always recommend places like Julian, Ramona, Anza Borrego, which are close enough to San Diego for you to get to easily. But Anza Borrego in particular is a designated international dark sky site, which means that the communities in the area have put in the proper lighting with the shielding and stuff like that to protect their nighttime sky. Um, San Diego itself is sort of an interesting place because if you're on the beach and you don't have a marine layer, there's nothing out to the west. So you can actually get good dark skies directly along the coast. We're almost more at the mercy of the marine layer in many ways than light pollution. And then your goal is just to try to get far away from a city. So far northern California can also be, because there's no large population centers north of Sacramento and San Francisco. It's just a matter, once again, of whether or not the weather's going to cooperate.
Yeah.
Yeah.
Well, that's always the question, isn't it?
Yes. Yes.
When you mentioned the visible confirmation of relativity, I saw a movie lately. It was called Einstein and Eddington, and the movie was about Eddington going out to that eclipse and seeing it.
Yeah.
And up until right before the eclipse, the sky was just completely filled with clouds, and they were scared that they wouldn't be able to see anything. But it cleared up.
Yeah.
So
Because I think that was even their second attempt too, because I think the
yes,
previous yeah.
it was. So you just never know, you know.
Because they were so ready to prove Einstein wrong.
Yes.
I don't think people realize how hungry people were to prove him wrong.
Yeah, I recommend that movie. I thought it was quite interesting from a science standpoint or a science history standpoint that I just didn't know much about. So I thought it was great. It's called Einstein and Eddington for
Okay.
anybody who wants to look it up. I know we had a couple of more questions come in, but we are quite a little bit over time. Lisa, it's up to you if you would like to answer them or not.
Well, I'm skimming over real quick, and it looks like they're all really related, and I could probably get to them pretty quickly.
Perfect.
So basically, can we escape a black hole? Not once you're caught. Once you're caught, you're done. So your goal is to not get caught. Can stars get pulled into black holes? Yes, absolutely. We've even made detections of radiation of electromagnetic radiation that looks like it's coming from stars getting pulled in. And how many black holes have we discovered? um I don't want to say millions because we haven't actually detected black holes in the, it's easier to detect black holes in the centers of large galaxies just by the ways that we do. But for supermassive black holes in particular, um we for galaxies that are large enough for us to do the research, we have found them. And then for smaller stellar sized black holes in our own galaxy, I'm not going to say millions because once again they're really hard to find, but we have discovered many. I'm not going to give a number, but many. So we are comfortable with our techniques to find them in the right situations. But black holes just hanging out on their own are hard to find, and so there needs to be an accretion disk or stars around them to look for them that way.
Perfect. Well, thank you so much for taking the last questions. And thank you everybody for joining us tonight, for spending a little bit over an hour with us discussing astronomy and the night sky and massive black holes. I thought it was super fascinating. I hope you enjoyed it as much as I did and as Lisa did, because I could see her passion talking about it. So I know Lisa had a good time
Yes, thank
with
you.
all of us. I hope we'll see you again next month for Sky Tonight. Just a reminder, that's planetary atmospheres on March 3rd. And then we're going to look at space junk on April the 7th. And we have many other science talks coming up. Just keep an eye on our website or follow us on social media. This way you won't miss any of our scientific lectures, talks, and presentations that we have while we continue to hunker down and be safe and be healthy. With that, I'm going to wish you all a wonderful good night and all the
Thanks,
best to all
everyone.
of you.
Good
Thank you so
night.
much.